Welcome to the Audio Club. For the first episode, I thought that we are going to do some introduction on sound. I tried to look up videos on YouTube and material on how you can visualize or imagine sound waves to understand how music is being produced, what do we need to make a recording, what kind of parameters we need from the speakers to reproduce those sound waves, but I really haven't found anything helpful. And I want to make now a little presentation and that is helpful for everyone to visualize, so you don't need a degree in physics to get the ideas. So I will not be using specific terms or really complex equations or whatnot, but rather trying to make it useful and digestible for everyone, for the audiophile. And you can imagine this presentation, and I will have more, as continued education credits for audiophiles, something to improve your knowledge and skills so that you are not just a passive consumer who is addicted to the absolute sound and stereophile and a couple more of the online newspapers coming out which really mimic these two giants, but they want to write their own reviews, their own perspective, but essentially they are kind of doing the same thing, just by a different crowd. What I want to do with these little audio clubs is to bring back the feeling of having an audio club that we have, but during these times, during this month, this year, so far, most of the year, due to the pandemic, everyone is forced to live without audio clubs, and I'm talking specifically here about our Hawaii audio club community, those people who tune in from different parts of the world. I have to tell you that here on Oahu in Hawaii we have a very strong audiophile community, and there are regular audio clubs, and I have to admit that during the past 6 years or so I have really neglected to join the club because my work has been just super crazy and super demanding, and I kind of fell off the radar. But now I want to just share a lot of things with all of you. And first of all, let's start with what sound is. So imagine the sound waves as waves in a fluid. We can imagine the high frequencies as waves that you create in a glass. So if you flick the edge of the glass of your wine or water or whatever fluid, then you will see ripples inside, and then in the center you see the smallest ripples. The diameter of those might be about like 1.5 centimeters or 2 centimeters. So if that was air and not water, that would correspond to about 22 kilohertz sound. So that's the dimension of a 22 or 20, about those really high frequencies that we can most people cannot hear them at all, but young children do, and there are some conductors and some people with really gifted hearing who can hear up to 20 kilohertz, and it means that their ears can pick up sound waves which are less than 2 centimeters long, and then as we age our hearing is degrading, so we can what's going on here? So Well, no, it just destroyed my pen tool. So let's go back here, and PowerPoint is not happy. I say laser pointer. Okay, it took away my pointer. So now we are back, and so if you see, like here, no, it doesn't work. Okay, so let's just talk about it. So the smallest ripples at the center correspond to the very high frequency waves, and towards the edge of the glass we can see waves those which have like a really big wavelength, really big distance between the ripples, and those would correspond to about 4 or 5 kilohertz. So we can imagine the high frequencies as really tiny waves between 5, 6, 7 and 2 centimeters. When we look at the mid-range, we go from a glass of wine to a tub. So imagine that you drop a watermelon in your bathtub and it creates big ripples. So the size of those waves corresponds to the wavelength of the sound waves for mid-range frequencies, and those are at the order of half a meter to a few meters. So you can see there are some smaller ripples and some big ones, and now you see the size has increased. There's more energy with those waves, but when you go to the really deep sound, let's say like 30 hertz to 20 hertz or subsonic frequencies, those correspond to really long wavelengths, really big waves, and we are talking about ocean waves. So when you look at this wave, I try to use my pointer. No, it doesn't work. So let's just go back. So maybe I go and point myself. So the whole length of the wave, that defines basically the energy that's pushing the wave. However, the wavelength is not this length that we see, but the length of a crest, and also the dip that follows the wave. So that's like a full wavelength, and what we see as the blip, that's half a wavelength. And indeed, if you are listening to some music at a I would say at a quiet normal volume, if you want to hear high frequencies which are the size of these tiny ripples, and you have 20 hertz material on the same recording, then the energy of that needs to be the same as an energy of a giant ocean wave. So translated to decibels, at the lowest levels of audibility, we need plus 50 dB at 20 hertz compared to a kilohertz. That's our ear. That's how our ear works. So our ear thinks that the volume level is the same if the 20 hertz wave has 100,000 times more energy than the kilohertz wave. So so this is the reason why it's super duper hard to create low energy sounds. So to go down to below 40 hertz to reach 20 or even reach subsonics. So that's an almost impossible task. And what you see here is there is a long wave, and there's a crest which is overtaking the wave. So what happened here is that there was probably a huge rock underneath and on the ocean floor, and as this giant wave is coming, that protruding rock caused an increase in pressure, and a piece of the wave just because of that increased pressure, just overtook the majority of the wave. And this is what happens in a port. So imagine that you have your subwoofer, which is supposed to create, let's say, a 20 hertz wave. However, a 20 hertz wave is 16 meters long. And the last time I have checked any subwoofer ports, they are just a few inches in diameter. So how do you squeeze a 16-meter wave through a 3-inch port, even if it's a 4 or 5 inches diameter port? It's ridiculous. It's like trying to squeeze through an ocean wave through a PVC pipe. You cannot. And this is what happens in real life when that 30 hertz or whatever deep sound wave that is coming out and at an extremely high pressure, it's going to make almost like a mini sonic explosion as it erupts into the air of your room. So there's a huge pressure wave being squeezed through those few inches diameter, and then it just suddenly erupts. And here you can see at the edge, at the crest, let me see if you can hear these tiny ripples as it's breaking, and then you see some extra big waves, big ripples here. This is what happens at your subwoofer port. So those are those unwanted frequencies which accompany the fact that they are being squeezed through that tiny sphincter. So that's this is what we get for abusing physics, for trying to make sound waves which are 30 feet long by a cube, which is about a foot by a foot by a foot diameter, and it has a tiny PVC pipe inside with a 3, 4, 5 inches diameter hole on it. So that's partially a reason why subwoofers sound so artificial. And when you get a really big sub, which is not just 1 cubic foot volume but much bigger, then those start to sound much better, because the air pressure differential ratio is not so great with them, so they don't have to squeeze out the tremendous energies through that tiny little hole, but they have more space. So I'm going to show you something like that. Let's see. So here we have these Altec speakers, and look at that. That's actually half of the port. The other half is on the back side. So if we look through, maybe if I get some extra light here, maybe let's go on this side, and if you look, you can look through to the other side of the speaker. So that's the downside. So the port is actually firing down, and this is the exit. So we have actually a 52 inches wide port. So instead of those long waves having to squeeze through a 3-inch size tiny sphincter, they have over half a meter to come through, plus half a meter on the back. So that means that they have a total width of a little over 1 meter. So it means that sound frequencies down to 80 hertz can come through unmodified by the port. So they are untouched. When we are thinking about the 3-inch diameter port, we are talking about frequencies of 400 hertz. So under 400 hertz, our subs start to distort and go into that pressure mode where you have that gigantic outburst. And that's why when you use subwoofers, then you hear the sound as it's like really muffled or pressurized or artificial and boomy. So this gives the boomy quality because there are miniature sonic booms happening all over. And as you see here, that's supposed to be a single low frequency wave, and now it breaks up to all kinds of frequencies. Those tiny pearls, they correspond to, if this is, let's say, a 20 hertz wave, those in size correspond to a 20 kilohertz wave. And that corresponds to, let's say, about 160 hertz or something like that. And that's what happens with subwoofers too, is that you have a lot of extra noise coming out. And even worse, because of the subwoofer cabinet or any other speaker cabinet, because that's not just true for subs, but any kind of ported speakers, whatever cabinet resonances are on the inside, they are going to get squeezed through immense pressure. And that's why ports have these secondary emissions as well, so that there are high frequencies coming out. And that's why it's a bad idea for speakers to have ports on the front, because when you have the port on the front, you have these high frequencies rushing at you, being propelled to you at tremendous speeds, and it's going to muddy the presentation. So what we can do as speaker designers to get rid of that problem is to, first of all, use, for example, what I have done here with these big ones is that the cabinet itself houses the Altec 515C driver, and it's being crossed over at 265 hertz. So it means that there are no high frequencies present in the sound, in the output. So whenever I'm squeezing through, so the driver is squeezing through air pressure through the port, there is nothing above a kilohertz or so coming through. So when I crank up the speakers, or I'm in the amp and I'm listening, I put my ear into the port, I don't hear any sound at all coming from there. So there are no high frequency reflections whatsoever. So the port itself is tuned to below 20 hertz. According to the measurements, it's 17.8 hertz tuning, and so it means that it has a high frequency cutoff of 40 hertz. So really, this port works at 40 hertz. This baby speaker next to it is 10 times smaller than the big one. So it means that this is 1 cubic foot internal air volume, and the big ones are almost 10 cubic feet free air volume. And they, this is literally the tiny version of the big one. So it also uses an Alnico speaker. It has the same similar internal structure, port firing down, but it's a much more simplified design, and it's a really small scale of the big boy. And here what I have added is also a port firing into the front, but on the bottom. So most speaker designs have the port close to the driver on the front, because then that adds more impact, because you can feel the air pressure right gushing at you from high up. And most people put those small speakers, let's say you have a small speaker with a front port on a stand, then the port will be at your chest level, or at the level of your face and firing at you. So then you will feel the impact in your chest. A better choice is to move the port to the rear of the speaker. In that case, you do not hear these secondary frequencies, which are the cabinet resonances being squeezed through at really high pressure. However, you also lose that chest impact. So that's one design consideration where you want to put your ports. The other consideration is that if you put the front port on the front, then apart from that added impact, you also have the freedom for speaker placement. Because in that case, you can put your speakers to the wall and they will be fine. If the port is firing back, then you are limited with speaker placement. You cannot put the speakers close to the wall because then they will become boomy. So when you are looking for a new pair of speakers, just consider that when thinking about front ported or rear ported, is that in case it's front ported, you have more choice, more freedom for speaker placement, but you will have also a little bit more muddy mid-range and not as clear. And the muddiness in the mid-range will increase with increased volume. So if you play your speakers quiet, then there's very little pressure building up, and the pressure is not big enough to create that outburst. And when you play your speakers loud, that's when you will start forming that gigantic spray of water. So let's just go to the next picture. This is more like a cleaner wave, which is still crushing at the end. And you usually have this thing happening, that the wavefront will start crashing down because there are room limitations. So the size of your room depends the volume of bass and other frequencies you can listen to. Because if the volume is, let's see on the next picture, so here in this area you can see those long nice clean waves, but here you see the crest forming and the wave is just crashing down. It's because the amplitude of the wave there was just too big. Actually what happened there is that there was a rock underneath at the bottom of the ocean, and that increased the pressure, so that increased the height of the wave, and then it came crashing down. So this happens in your bedroom if you are playing music too loud. So that's why if you want to play loud music, first of all you need a big room. So let's say that you have a small bedroom, then in that small bedroom there's a severe limitation on the volume you can play, and also a severe limitation on the lowest frequencies that are possible to create in that small bedroom. So imagine this scenario. This is a huge church. This is a huge basilica in Esztergom in Hungary, and this thing is, I think, like at least 70 meters long, the main hall, which would be over 200 feet, and it's about, I think, about 60 meters tall or something. It just insanely big. So if you just look at that wave on the side, yes, you could even squeeze a tsunami inside this building. So that's why the church organs are placed in these monumental buildings, because they have space enough to form those extra long sound waves, those 20 hertz and even lower waves. So for example, this church could house even like a 5 hertz sound wave would fit in there. So if you have a church organ, normally the lowest C is 32 hertz, and if there's a subsonic to that, it's at 16 hertz. Even a 16 hertz sound wave would fit in this church at least 4 times. So that's why organ sounds so good in a cathedral, because there's plenty of space to feed these gigantic waves in, and you can increase their energy because there is airspace enough to contain and hold this energy without distortion. Now try to do the same thing in your bedroom. If you want to squeeze those tsunami like 20 hertz sound waves in your bedroom, you are going to get just washed out. So if it was water, not air, your house would be destroyed. And that's true for the sound as well. There's no way to squeeze in 20 hertz into a small bedroom. If your bedroom, eventually any kind of room you have, the lowest frequency sound you can reproduce in that room depends on the longest dimension of your room. So if your room has a dimension of about 16 feet, then the lowest frequency that you can play undistorted is 40 hertz. And then if you have like double that, like the longest dimension of your room is at least 32 feet, then you can go down to below 20 hertz or so. But if you have a small room, then do not try to force 20 hertz into that room, because you will get just boominess and overloaded room. So if you have a small room and small speakers, your solution to go down to 20 hertz instead of 60 is not getting 4 subs and putting a sub in each corner, because that will just massively overload the room and it will sound terrible, and you will never get anything close to 20 hertz, not even 40 hertz. What you need is a decent sized room. So with that, I shall conclude the first part of our audio club episode, and we shall continue at the next part with how to choose speakers and amps, how to match an amp with a speaker. So right now, just get a cup of tea and put on your favorite music and relax. Thank you for listening.